Okay, in this lecture we're going to cover the second half of our section 2.5 material on equations of lines and planes in space. So in the first part of this section we had talked about equations of lines in space, and we saw that a line could be defined by a point on the line and a direction vector. Now, to define the equation of a plane in space, we need two things. So similarly, a plane in space is determined by a point x0, y0, z0, which lies in the plane, and a vector n that is orthogonal or perpendicular to the plane. And this orthogonal vector, which we denote as n, is called a normal vector to the plane. So in general here, since we're talking about a vector in space, this normal vector n, which is orthogonal to the plane, will have some components of the form a, b, c, where a, b, and c are real numbers. So let's try to visualize this and think about how we could find an equation of a plane passing through a given point that has a normal vector. So in three-dimensional space, we have our x-axis, our y-axis, and a z-axis. And let's say that we're looking at some plane in space. So here we might have something that looks like the following. Of course, this extends infinitely in all directions. So if we have for this plane some point which lies on that plane, let me call it x0, y0, z0, then for any other point on this plane, let's call this other point x, y, z, any other arbitrary point, we could find the vector from x0, y0, z0 to the point x, y, z. Let me call that vector maybe v. So here we could say a vector that lies entirely in the plane would be the vector which I'm denoting as v, which has its initial point at x0, y0, z0, and its terminal point at some arbitrary point x, y, z that lies in the plane. So the coordinates, or the components of that vector, would be x minus x0, y minus y0, and z minus z0. Now, we were also told that a plane is defined by a normal vector. So that is some vector that lies orthogonal to this plane. So since the vector lies orthogonal to the plane, we can visualize it. It's like sticking out from the plane at a 90-degree angle. So it would be orthogonal to the vector v that lies in that plane. So here, let's say, since this vector v, which lies in the plane, and our normal vector to the plane n are orthogonal, the dot product of those vectors, that is n dot v, would have to equal 0. So let's write out the dot product of n and v. The product of the first components of these vectors would be a times x minus x0 and then we add the product of our second components, which would be b and y minus y0, and then we add the product of the third components, which would be c and z minus z0. And that has to equal 0. So this equation which we've derived for any arbitrary point x, y, z, which lies on our plane gives us what we call the scalar equation of the plane passing through this point x naught, y naught, z naught with a normal vector in whose components are a, b, c. So this is the equation which we've just derived. Now, if we were to expand this equation and group all of our constant terms together on one side of the equation, we could express this same equation in the form ax plus by plus cz is equal to some constant d. And this form for the equation of a plane is called the standard form for the equation of a plane. So that's what we will use most often. So now that we've derived a formula for the equation of a plane through a point with a given normal vector, let's look at some examples. So in this first problem, we're asked to find an equation of the plane through the point 2, 4, negative 1. So this point is our x naught, y naught, z naught, with a normal vector in given by 2, 3, 4. So this is the normal vector a, b, c. And then we're also asked to find the intercepts of this plane and sketch the plane. So let's start by finding the equation of the plane. So here I'll say first, the equation of the plane would be given by a, the first component of our normal vector, which was 2, times x minus x naught, which was 2, plus the second component of our normal vector, which is 3, times y minus y naught, which was 4, and then plus c, the third component of our normal vector, 4, times z minus z naught. Now z naught was negative 1, so we get a z plus 1, and this is equal to 0. So if we're interested in rewriting this equation in standard form, let's see how to do it. So expanding or distributing all of my constants through this equation, I would have 2x minus 4 plus 3y minus 12 plus 4z plus 4 is equal to 0. So grouping my constant terms together, well, I have a negative 4 minus 12 and a plus 4. So the negative 4 and plus 4 cancel. And then moving this negative 12 term to the right-hand side of my equation, I would be left with 2x plus 3y plus 4z is equal to 12. And this now has the standard form for the equation of a plane. Now from here, we were also asked to find the intercepts of this plane and sketch the plane. So when we're talking about the intercepts of the plane, we're talking about where this plane will cross the x, y, and z axes. So here to find the intercepts, for instance, to find where our plane crosses the x-axis, well, for every point on the x-axis, both y and z are equal to 0. So looking at the equation of my plane, if I set y and z equal to 0, I would have 2x equals 12, and so x is 6. So the intercept of my plane with the x-axis would be the point 6, 0, 0. To find where my plane crosses the y-axis, I could take the equation for my plane and set both x and z equal to 0. That would give me 3y equals 12, and so y is 4. So 0, 4, 0 would be where this plane crosses the y-axis. And to find where it crosses the z-axis, we could set both x and y equal to 0 in the equation for our plane, and we would have 4z equals 12, so z is equal to 3, and 0, 0, 3 would be the z-intercept. So let's see how we can use these intercepts to sketch our plane. I get some sort of visualization for what this looks like. So here in the first quadrant of space, we have our x-axis, y-axis, and z-axis. And we found that the x-intercept was 6, 0, 0. Our y-intercept was 0, 4, 0. So it doesn't intersect along the y-axis quite as far out as it did along the x-axis. And then for our z-axis, we had an intercept of 3. So the part of the plane that lies in this first octant would be shown here. So this gives us a little visualization of what exactly our plane looks like in this first octant, and of course it extends infinitely in all directions. But finding these intercepts allows us to visualize what our plane would look like in 3 dimensions. So let's look at some other problems involving planes. So another classic problem in a Calculus 3 course would be something like the following. We want to find an equation of the plane in standard form that passes through the points A, B, and C, whose coordinates are given. So we want the equation of a plane which contains 3 points in space. So let's think about how we're going to find it. There's 2 things that we need for the equation of a plane. We need a point that lies on the plane, and in this example we're given 3 points on our plane. And we need a vector which is normal to the plane, or orthogonal to the plane. So let's consider how we're going to find that. Here, if we have 3 points in space, call them A, B, and C, and we're looking for the equation of the plane which contains those points, well, we need a vector which is normal to this plane. So to find it, we could take 2 vectors in our plane, perhaps the vector from A to B and from A to C. And I know if I take the cross product of those 2 vectors, well, the cross product of 2 vectors is orthogonal to both of those vectors. So if both of those vectors lie in the plane, then the cross product would be orthogonal to the plane, or a normal vector to that plane. So that's our approach here. Let's start by finding 2 vectors in the plane. So here, I'll say 2 vectors in the plane would be the vectors AB, whose components would be given by 1, -5, 1, and AC, whose components would be 2, -1, -5. So by taking the cross product of these 2 vectors, I would get a normal vector to the plane. So let me say a normal vector to this plane is given by n, which could be taken as the cross product of AB with AC. So that is given by the determinant of a 3x3 matrix whose first row consists of the standard basis vectors I, J, K, The second row would consist of the vector AB, which was 1, -5, 1. And our third row would be the vector AC, which was 2, -1, -5. So for the I component of this cross product, we would have 25 minus -1, so 26. For our J component, we would have 2 minus -5, which is 7. And for our K component, we would have -1 minus -10, which would give us a 9. So now I have a normal vector to the plane, and I have at least one point that lies in the plane. So I'm ready to find my equation. Now I can use any of the points A, B, or C in the plane to substitute into my equation. So here I'm just going to work with the first one, point A. So using the formula for the equation of a plane which we derived, we would have the first component of our normal vector, 26, times x minus the first coordinate of the point A, which was -1, so we'll have an x plus 1, plus 7, the second component of our normal vector, times y minus the y component of the point A, which was 2, plus the third component of the normal vector, which was 9, times z minus the z coordinate for the point A, which was 1, and this must be 0. Now, to express the equation of this plane in standard form, we need to distribute all of our constants. So we would have 26x plus 26 plus 7y minus 14 plus 9z minus 9 is equal to 0. And then we'll group all of our constants together. So here we had 26 minus 14 would be 12, minus 9 would be 3. So if I move all of my constants to the right-hand side of the equation, I would be left with 26x plus 7y plus 9z is equal to -3. So this would be the equation of that plane in standard form, which contains these 3 points, A, B, and C. So let's look at our next one. In this next example, we're asked to find the point at which the line with parametric equations, which are given here, intersects the plane whose standard form equation is given. So a problem of interest might be to determine where a line in space crosses a plane in space. And in order to find the intersection of a line with a plane, well, we know the parametric equations for our line, x, y, and z, must all be satisfied, and the equation of this plane must also be satisfied. So what I can do is substitute these equations for x, y, and z into the equation of my plane, and I'll get it down to a single variable t. And then I can then solve for t and substitute into my parametric equations to find that point of intersection. So let me start by saying here we're going to substitute the parametric equations of the line into the equation of the plane. And so let's see what we have. So the equation for our plane was 4x, where x is given by 2 plus 3t for points on that line. Then we had a plus 5 times y, where y was -4t, and then minus 2 times z, where z is 5 plus t, and that must be equal to 18. So expanding, let's see what we have. We've got an 8 plus 12t minus 20t minus 10 minus 2t is 18. So let's start by grouping all of our t terms together. We had a 12t minus 20t, which would be negative 8t, minus another 2t, gives us negative 10t. And then grouping all of our constants together, well, we had 8 minus 10 is negative 2 on the left-hand side of this equation. If we add 2 to both sides, then we would have this negative 10t is 20. So it follows that t is negative 2. So once I have the value for t that represents the point of intersection of our line with our plane, to get the x, y, and z coordinates for that point, I can take this value of t and substitute into my parametric equations for x, y, and z. So here, I'll say substituting into the parametric equations, the point of intersection is the point x, y, z. So substituting in negative 2 for t, our x equation would be 2 minus 6, so negative 4. Y is negative 4 times t, which would give us a positive 8. And then z is 5 plus t, which would give us a 3. So this is our point of intersection for the line with that indicated plane. So let's move on a little bit and ask ourselves what it means for two planes to be parallel. So in the first part of this section 2.5 material, we said that two lines are parallel to one another if their direction vectors are parallel. That is, if the direction vector of one is a scalar multiple of the other. So for planes, we would say that two planes are parallel if their normal vectors are parallel to one another. So here, if the normal vectors are parallel, then the planes are considered to be parallel. Now, in the event that two planes are not parallel, then they intersect one another in a straight line, and we might be interested in the angle between two intersecting planes, which will be defined as the acute angle between their normal vectors. So for two planes which do not have parallel normal vectors, those planes will intersect in a line in space, and we would define the angle of intersection of those two planes as the angle between the normal vectors for those planes. And we know how to find the angle between two vectors in space. So let's consider a problem like this. We're asked to consider the planes defined by these two equations in standard form. And in part A, we're asked to find the angle between these planes. So that implies that they are not parallel, that they would be intersecting here. So let's start by considering the normal vectors for these planes. So here I will say that the normal vectors for these planes are, for the first plane, in 1, and the normal vector can be found from the equation of the plane. Let's review how this might be done. So if we have the equation of a plane in standard form, these coefficients for x, y, and z are what we were calling a, b, and C, which would be the normal vector for that plane. So if you have the standard form for the equation of a plane, you can find your normal vector immediately. So for our first plane, we would have a normal vector of 4, -2, 1. And for the normal vector to the second plane, we would have 2, 1, -4. And we can see pretty clearly that these two vectors are not parallel. One is not a scalar multiple of the other, which implies that our two planes are not parallel. Now, to find the angle between these planes, we need to find the angle between these two normal vectors. And so we need to compute a couple of things to find that angle between these vectors. The first thing that I need is the dot product of these vectors, n1 dot n2, which would be given by, let's see, 8 minus 2 minus 4, which would leave us with 2. And I need the magnitude of these two vectors. That is the magnitude of n1, which would be the square root of 16 plus 4 plus 1, so root 21. And the magnitude of n2, which would be the square root of 4 plus 1 plus 16, which would also be root 21. So using the formula that we had for the angle between vectors in terms of the cross product that we saw in section 2.3, if theta is the angle between these normal vectors, which is the angle between the planes, then cosine of theta is given by the dot product of our two vectors, which was 2, divided by the product of the magnitudes of n1 and n2. Now, since they were both square root of 21, when we multiply root 21 by itself, we're left with just 21. And so to solve for theta, we could take the inverse cosine of 2 over 21, which would give us our angle measure in radians, or by converting to degrees, we would have 84.5 degrees approximately. So here would be our angle measure in radians, or approximate value in degrees. Now in part B, we're asked to find parametric equations for the line of intersection of these two planes. So as we were saying, if we have two planes in space which are not parallel, then they intersect at one another, and the intersection of two planes would be a line. And what we're interested in is parametric equations for that line. So recall from the first part of this section, in order to find parametric equations for a line in space, we need two things. We need a point on the line, and we need a direction vector for that line. So first, let's try to find a point on the line of intersection. So here, the easiest way to do this might be to consider where that line of intersection crosses one of our coordinate planes. So let me start by saying this. First, we need a point on this line of intersection. So one way that we could find such a point is to see where this line crosses the xy plane. Now the xy plane is the plane defined by z equals to 0 for any point in the xy plane. The z coordinate must be 0. So to see where this line, which lies in both planes, crosses the xy plane, we can set z equal to 0 in the equations for these planes. So for our first plane, we would have 4x minus 2y is equal to 2. And for the equation of our second plane, if we substitute z equals 0, we would have 2x plus y is equal to 3. So let's see if we can solve this system of equations for x and y. So a few ways that we could go about doing this. One thing that I might do would be to multiply my second equation by 2 so that I have a 4x plus 2y. And then if I add those equations together, well, I would have 4x plus 4x would give me 8x. And then my negative 2y plus 2y would cancel one another. And I would have that is equal to 2 plus 6, which would be 8. So it follows that x is equal to 1. And to find y, I could substitute this value of x back into either one of these two equations. Now looking at my second equation, I can see that y would be 3 minus 2x. So if x is 1, then y would also be 1. So what we found is the following. A point on the line of intersection is the point 1, 1, 0. Now, something else that we need to find the parametric equations of a line in space is a direction vector. Now, if we're talking about the line of intersection of two planes, then our direction vector would have to be orthogonal to both normal vectors of these planes. So since the normal vector of a plane is orthogonal to the plane itself, and the line of intersection must lie in both planes, the direction vector, or the line that we're talking about, must be orthogonal to both normal vectors for these two planes. So here we could say a direction vector for our line of intersection. It would be given by, let's call it v, which could be taken as the cross product of the normal vectors n1 and n2 in order to get a vector that's orthogonal to both n1 and n2. So this would be given by the matrix, the determinant of the 3 by 3 matrix, whose first row consists of the standard basis vectors I, j, k, whose second row would be the first normal vector n1, which was 4, negative 2, 1, and whose third row would be the second normal vector 2, 1, negative 4. So for this cross product, our I component would be given by 8 minus 1, so 7. Our j component would be 2 minus a negative 16, or 2 plus 16 is 18. And then our k component would be 4 minus negative 4, which leaves us with 8. So now what we have is a point that lies on the line of intersection and a direction vector for that line of intersection. So from here, we can find our parametric equations for this line, which would be given by x equals 1 plus 7t, y equals 1 plus 18t, and z equals 0 plus 8t. So these would be parametric equations for that line of intersection of these two planes. Now the next thing that we'll talk about in this section is the distance from a point to a plane. So in the first part of this section, we had defined lines in space, and we found a formula for the distance from a point to a line. So what about the distance from a point to a plane? So we have the following theorem for that distance formula, which says that the distance from the point x naught, y naught, z naught to the plane whose equation is given by ax plus by plus cz plus d equals 0 is given by the following. So here we'll use capital D for distance, and it's given by the ratio where our numerator is the absolute value of the equation of this plane, but with the point x naught, y naught, z naught substituted in for x, y, and z. And then we divide by the square root of the sum of a, b, and c squared, where a, b, and c would be the components of the normal vector to that plane. Now the proof of this formula works fairly similar to the proof for the formula for the distance between a point and a line in space. So making use of this new formula, let's consider the example of finding the distance from the point given here to the plane whose standard form equation is given. Now, one thing I'll mention, sort of something to be aware of, is that in this distance formula, the equation of our plane is expressed as the sum of these terms is equal to 0. So something that we might want to do for these types of problems is always move all of our expressions to one side of the equation. So if I subtract 5 from both sides, then I have the equation of the plane written in the form that's given in that theorem. So let's see if we can find this. So here, our distance from the point to this plane is given by the absolute value of the equation of our plane with the indicated point substituted into it. So I would have 4 times x, which was 3, minus 6 times y is negative 2, and then plus z, which was 7, minus 5. And then we are dividing by the square root of the sum of the squares of these components of our normal vector. So here, looking at the equation of our plane, the normal vector would be the vector 4, negative 6, 1. And we're looking at the length of that normal vector, or its magnitude, which would be the square root of the sum of the squares of its components. So here, the square root of 16 plus 36 plus 1. So in our numerator, we have the absolute value of 12 plus 12, and then our plus 7 minus 5 would be plus 2. And we're dividing by the square root of 16 plus 36, which would be 52 plus 1, would give us 53. So in the numerator, we have the absolute value of 24 plus 2 would be 26, and then over the square root of 53. So this would be the distance from that point to our plane. So a little visualization here of the idea. Let's say we have some plane in space, and we have a point, x naught, y naught, z naught, that lies somewhere off of that plane. We're looking at the shortest distance from that point directly down to our plane. Okay, so let's look at one last example. In this last problem, we're asked to find the distance between the parallel planes given here. So first, before we jump into this problem, let's just review how we might verify that these planes are parallel. So we could look at the normal vectors for these planes. So the normal vector for our first plane would be 2, -2, 1. And the normal vector for our second plane would be given by 4, -4, 2. And these two planes are parallel if their normal vectors are parallel. So let's show that they are parallel. So comparing the first components of these normal vectors, well, to get from 2 to 4, I would have to multiply the vector n1 by 2. So let's see what happens if we multiply the other components by 2. Taking -2 times 2 does give us a -4, and taking 1 times 2 does indeed give us 2. So we can say here, since the vector n2 is equal to twice n1, the planes are indeed parallel, since these two normal vectors are parallel. So to find the distance between parallel planes, well, we could choose any point on one of my planes and then find the distance from that point to the other plane. So let's say here to find the distance between these planes, we can choose any point on one plane and find its distance to the other plane. Let's see how we could find a point on one plane. So to get any point on our first plane, we could make any choice for two of my variables. So let's say if we let y and z equal 0 in the equation of the first plane, then we would have 2x is equal to 10, and so x equals 5. So the point 5, 0, 0 lies in the first plane. And then to find the distance from this point, 5, 0, 0, to our second plane, we could use the distance formula, which we had just considered. Now, the equation for our second plane, I'm going to rewrite as 4x minus 4y plus 2z minus 2 equals 0. Because I want the form for the equation of my plane to be some expression equals 0 as we had in that distance formula. So here the distance, capital D, from the point to this line would be given by the absolute value of the equation for our plane with this point plugged in. So 4 times x, which was 5, minus 4 times y, which was 0, plus 2 times z, which was 0, minus 2. And then we divide by the magnitude of the normal vector. So for the second plane, our normal vector was 4, negative 4, 2. So its magnitude would be the square root of 16 plus 16 plus 4. So let's see what we have here. In the numerator, we have a 20 minus 2, which is 18. The absolute value of 18 is 18. And then we're dividing by the square root of 32 plus 4. So that is root 36, or 6. And then 18 over 6 leaves us with 3. So this would be the distance between those two parallel planes, 3 units.